Okay, thank you for joining me today. We will start another topic related to double reinforced section. Just to give you a reminder, previously, and this is the typical cross-section for reinforced concrete, your cross-section will have only reinforcement on the tension side. And for the compression side, concrete will be enough. So in this case, your concrete is under compression with a stress block, looks like this, with depth A, and we have another depth for the neutral axis called the C, and this C equal beta 1 time A. And we have tension on the steel reinforcement, capital T, and we can convert the compressive stress to capital C. So capital C equal 0.85 F prime C A B, and the capital T equal area steel time F yield. This is the case of single reinforced section. We have two parts. Part of the concrete is working under compression, and the part of the steel reinforcement is working under tension. And any other part in this cross-section is cracked and trashed. That makes sense? We have another case. If this concrete, is not enough to support compression for many reasons. One of them, I will ask you, hey, go ahead and design a concrete section with maximum thickness equal 50 inch. You cannot increase this cross section more than 50 inch. You tried your M ultimate. You tried M ultimate divided by phi BD square. Unfortunately, your value is outside the table. Do you remember the design tables that I gave it to you to find out the value of rho? If your value is outside the design values for the rho and then your steel reinforcement, that means this depth of the cross section is not enough to support this M ultimate. What you mean by not enough? I mean the concrete is not enough, because this depth 50 represented the concrete. So this concrete will not be enough to support M ultimate. If you cannot increase the 50 for any reason, clearance height, whatever the reason, then we have to give a hand to the concrete. What you mean by give a hand to concrete? I mean, I will provide compression reinforcement. At the same time, I have to provide additional steel reinforcement to the current. So if you have something here, you have to increase this one more and more and more equal to what you did here. In this case, your cross section is called double reinforced section. The concrete, which is not enough to support your compression, I provided a hand. I provided more material, which is steel reinforcement, to support or to share the compression with concrete. So just to give you some hints before starting, I would like to highlight. This area still is called AS. This area still will be called AS prime. So AS is the area of steel reinforcement in tension. AS prime is the area of steel reinforcement under compression. There is one more. We have this distance from the top to the tension steel reinforcement is called D. The depth is called the depth of tension reinforcement. We have another symbol here called D prime, which is the depth of compression steel reinforcement. And this distance is measured from the top to the steel reinforcement in the compression. Does that make sense? So we have area steel and area steel prime. We have D and D prime. Anything prime related to compression steel reinforcement. Any questions so far?
No, sir.
Then the technique to design your double reinforced section, everything will be given. I will figure out the design moment strength and make comparison with the M ultimate, and to make sure your design moment strength is greater than the ultimate moment, which is coming from structural analysis. So M ultimate is coming from structural analysis, from the dead load, life load, wind load, whatever. This one is coming from your design. How to figure out the phi MN? We have a technique here. This technique looks like the design of T section. Let me explain it a little bit, and then we can do an example. So please pay more attention. This technique is summarized in this slide, but I would like to start it from scratch. I will have my double reinforced section. I have more steel reinforcement at the bottom, and this area steel must be greater than the area steel at the top. And keep in your mind, we have a depth here called D prime, and we have another depth here called D. And we have this width B. This cross section can be converted to two parts. The first part is the concrete cross section with part of the steel reinforcement. I will call it area steel 1. Plus the compression steel area steel prime will work with some of the area steel, which is area steel 2. Keep in your mind, your area steel 1 plus area steel 2 must equal area steel. What I did, I divided this total area steel in tension. I divided it to two parts. Not equal, but two parts. Keep in your mind, to make balance for this part, to make balance, you have to say area steel prime must equal area steel 2. The area steel in the compression must be equal to the part of the area steel in tension. So I will start from this. Area steel prime is known. Must equal area steel 2. So I can figure out the value of area steel 2. Once you get the value of area steel 2 and you already know what is the value of total area steel, I can figure out the value of area steel 1. Does that make sense? For this part, I will have compression and I will have tension. the compression must equal the tension. That means 0.85 F prime C time B time A equal area steel 1 time F yield. From this equation, I can figure out the value of area of A. And keep in your mind the distance between the two forces is D minus A divided 2. So your nominal moment, part number 1, will equal capital T times D minus A divided 2. This is for part number 1. Piece of cake. Part number 2, I will have compression. I will label it C, capital CS. This one is capital C. You can call it capital CC. This is compression in concrete. This is compression in steel. It's up to you. Does that make sense? So I will have compression in the steel reinforcement, and I will have another tension in the part of the steel under tension. For acrobium, capital C must equal capital T. Capital C equal area steel prime time F yield. Capital T equal area steel 2 F yield. And this is the reason why I mentioned area steel prime must equal area steel 2. This is just for give you a hint. Why I said area steel prime must equal area steel 2. The part of steel reinforcement under compression must equal the part of the steel reinforcement under tension for this part. Why? To make sure we have a cropping. Because F yield equal F yield. And keep in your mind the distance between the two forces is D minus D prime. The distance between this steel rebar and this steel rebars is D minus D bar, D prime. So the nominal moment for part number 2 equal capital T, this one, time D minus D prime. Capital T in this case equal area steel part number 2 time F yield time D minus D prime. Once you get the nominal moment for part number 1 and the nominal moment for part number 2, I can say nominal moment for the whole cross section equal Mn1 plus Mn2. And if A for this type of cross section will be 0.9, I can figure out the value of phi Mn, which is the design moment strength. That makes sense? It's very easy. Just you need to understand I divided my whole cross section with double reinforcement to two parts. One part concrete with a little of the steel reinforcement in tension, and the second part your steel in compression with the remaining part of steel in tension. This part will give you Mn. This part will give you Mn. Then I will add them together to find the final value of the Mn. Keep in your mind, I assumed the steel in compression, area steel prime is yielded. This is my assumption. I assumed that the steel in compression is yielded. This assumption will be checked. If it's true, we are done. If it's not true, unfortunately, I need to repeat all of these calculations and follow up another technique, which is this one. So first of all, I'm assuming the compression steel reinforcement yielded. Then I did my calculation. Then I will check. Let's do an example, and I will show you how to do this check. We have this cross-section. Everything is given. Cross-section dimensions, everything. And we need to figure out what is the design flexural strength, phi Mn, for this double reinforced section. First of all, I need to make sure I have everything I need. Anybody can tell me what is the value of area steel? What is the value of area steel prime? What is the value of D? What is the value of D prime? Any help? What is the value of area steel? Guys, are you still here?
Is it gonna be 6.25?
Thank you. Yeah. Why you are hesitated? Yeah, 6.25. Thank you, Jasmine. 6.25, if this number is not given, you need to figure this out. We have 4 rebars, number 11. So you can open your table for number 11. What is the area for this size? And multiply it by 4, you will get 6.25. What is the value of area steel prime? Is 2 inches square. If you are not given this information, we have 2 rebar number 9. So you can figure out what is the size, what is the area of size number 9, then multiply it by 2. What is the total depth of the steel reinforcement? Keep in your mind, depth means the distance between the steel reinforcement in tension to the top of the cross section. Do you
24.
think this depth will be what?
24.
24, thank you. 24 inch. What is the D prime, which is the depth from the top to the steel reinforcement in compression? I think it's given 2.5 inch. These are the 4 parameters you need to figure them out before starting. Let's start. I will divide this cross section to 2 parts. The first part, your concrete, with some of the steel reinforcement in tension. I will label them area steel 1. Plus, the remaining part of area steel in tension will be area steel 2. Will work with the steel in compression, area steel prime. Keep in your mind, your area steel prime is 2 inches square. That means your area steel 2 must be 2 inches square also. That means your area steel 1 will be 4.25 inches square. That makes sense? We have a condition that in this part, area steel prime must equal area steel 2. And we understand that area steel 1 plus area steel 2 must equal the total area steel. So from this relationship, this one is 2, so this one will be 2. This one is 2, and this one is 6.25. Then I can say area steel 1 will be 4.25. Does that make sense? This is from the beginning. This is part number 1. This is part number 2. For part number 1, I will have my neutral axis. I will have compression at the top. I will have tension at the bottom. I can say capital C equal capital T. So, can start here. For part number 1, I said capital C equal capital T. So, F 0.85, F prime C time A time B equal area steel 1 time F yield. Your area steel 1 in this part, 4.25. What is the value of F yield? I think F yield is given 60 KSI or 60,000. It's up to you. I will say it 60, I'm sorry. Equal 0.85. What is the value of F prime C is given 3 KSI, 3. So I will use it 3. Time A, I don't know. Time B, what is the width of your cross section is given by 14. The only unknown in this equation is your value A. This A will be 4.25 times 60 divided by 0.85 times 3 times 14. I got 7.1 inch. Keep in your mind that the distance between the two forces in this part, this distance, equal D minus A divided 2. This is the normal that we learned before. So your nominal moment for this part will equal capital T, for example, time D minus A divided 2. Everything you need is given. T, capital T, equal 4.25 times 60,000. time depth, the total depth of this steel reinforcement 24 minus A 7.1 divide 2. I can find the value of MN1. It will be very big number because it will be in pound. Just a moment. Times 60,000 times 4.25. I got 5209285.7 pound inch. I can divide this number by 12,000. It will give you 434.1 kib foot. This is the contribution of part number 1, MN1. That makes sense? Part number 2, I will have compression in the steel reinforcement here. I can label it capital CS. S means steel. And I will have another tension here. You don't need to say the capital C equal capital T because they already equal. Does that make sense? I can say the distance between the two forces will be depth minus D prime. So the nominal moment directly for this part will equal capital T at the bottom times the distance in between. Your capital T at the bottom equal this area steel 2 times F yield 60,000 times your depth 24 minus D prime 2.5. From this one, I can figure out the nominal moment part number 2. It will be 2 times 60,000 times 24 minus 2.5. I got 25,800,000 pound inch. If you divide this number by 12,000, it will be 215 kib foot. But this is the nominal moment for part number 2 of the cross section. Since the two parts represent the total cross section, then your final nominal moment will be MN1 plus MN2. So I need to add 434.1 plus 215 will give you the total nominal moment. Equal 649.1 kib foot. Phi will be 0.9. So phi MN, the design moment strength, will be 584.2 kib foot. This is the design moment strength for this cross section if steel reinforcement in compression yielded. I need to check. If yes, we are done. And this is your design moment strength. If no, unfortunately, I need to disregard all of these calculations and start a new calculation. That makes sense? So how to check? It's very easy. How to check? This check is explained in this slide. How to check if the compression steel reinforcement yielded or not. I would like to start it from scratch because you're already familiar with this one. Believe me. Keep in your mind that we have a steel reinforcement here, area steel, and we have area steel here, area steel prime. This distance equal D prime, and this distance equal D. This D equal 24, this D prime equal 2.5 inch. This width equal 14. And we have a neutral axis. This neutral axis at distance C. Anybody in this room, in this meeting, can tell me what is the value of this C? the depth of the neutral axis, equal beta 1. I'm sorry. A equal beta 1 times C. Do you remember this expression?
Yes, sir.
Keep in your mind, you already got the value of A, 7.1. So your A is known, 7.1 inch. Beta 1, based on the given information about the F prime C, you should have a table for F prime C 3000 or 3 KSI. I believe your value of beta 1 equal 0.85. Do you agree?
Yes, sir.
So I can figure out the depth of the neutral axis. That will be 7.1 divided by 0.85. I got 8.4 inch. Keep in your mind that we have something called the strain distribution. Strain distribution means I will have compressive strain in concrete, tensile strain in steel, which is called epsilon T. And if you draw in between, you have to pass through 0 at the neutral axis. And we learned, according to ACI, this strain in concrete equal 0.003. I will focus on figuring out what is the strain in the steel reinforcement under compression. What is this value? Which is called epsilon C. Unfortunately, not epsilon C. It's epsilon SC. And this one will be epsilon ST because we have two steel under compression and the steel under tension. If you would like to figure out what is the value of epsilon SC, I need to do triangle similarity between this triangle and the biggest one, this triangle. Keep in your mind, this distance equal C minus D prime, which equal, leave it. And this total distance equal C. So I can say 0.003 divided by epsilon steel compression equal the total distance C divided this distance C minus D prime. Triangle similarity. So this C equal how much? 8.4. And this C 8.4, this D prime 2.5. The only unknown in this expression is the strain in the steel reinforcement under compression. So 8.4 minus 2.5 times 0.003 divided by 8.4, I got here 0.0021. This is the value of strain in compression steel reinforcement. We have a value called epsilon yield. If you remember this value, it was equal, I think, F yield divided by E steel. Do you remember that? If you go back to the previous modules, we have a value called epsilon yield, yielding strain of steel equal F yield divided by E steel. In this problem, F yield is given by 60 KSI. E steel equal 30,000 KSI. If you divided this number by this number, you will get 0.002. If epsilon steel compression that you got from the triangle similarity is smaller than or at least equal. I'm sorry. Is greater than or at least equal. Greater than or at least equal. Epsilon yield, then steel in compression yielded. And we are done. Do you remember what was the question? If the steel reinforcement in compression yielded, if yes, we are done. Yes, how to answer yes? If epsilon steel under compression is greater than or equal epsilon yield. The epsilon steel under compression is 0.0021. The epsilon yield is 0.002. So this number is greater than this number. Yes, steel reinforcement is yielded, and the Phi Mn based on my calculation equal this value 584.2. Keep foot. That makes sense? If no, if epsilon steel compression is smaller than epsilon yield, in this case, steel reinforcement in compression did not yield. And we need to disregard or ignore what we did. All of these calculations must be deleted, and we will start new calculations. This new calculation based on this slide. If the compression steel reinforcement did not yield, we need to follow these few steps to figure out the nominal moment 1, the nominal moment 2, and the final nominal moment. Then you can multiply the final nominal moment by phi equal 0.9. Very easy. It's not a big deal. Very easy. Don't worry. Just we need to set up this equation. And from this equation, I can figure out, actually, I cannot figure out anything because the steel reinforcement under compression did not yield. So I'm going to use this F prime C, F prime S. This F prime S will equal to this expression. Then I will use this expression back to the first equation. I will find myself with an equation with C, quadratic equation with C as an unknown. I can solve this quadratic equation to find C. Once you get the value of C, I can get the value of A. Then I can figure out the nominal moment as it is. Let me do an example and show you how to calculate the Phi Mn in the case of your steel reinforcement did not yield. We need only just to follow the equations in this slide. I have this example. We need to figure out what is the Phi Mn for this cross section. If you would like to follow the actual rules, I will start like this. Your area steel here equal 5.06 because this cross section is double reinforced section. Area steel prime equal 1.2. Your depth equal, I think your depth is the same, 24, and your D prime equal 2.5. So far, until this moment, I don't know if the steel reinforcement in compression yielded or not. So I will start from scratch. I will assume this cross-section is divided to two parts. The first part looks like this. With part of the area steel, I will call it area steel 1. With the concrete cross-section and the steel reinforcement in compression, area steel prime. With part of the steel reinforcement in tension. I will call it area steel 2. Keep in your mind, for the second part, area steel prime must equal area steel 2 must equal 1.2. Keep in your mind that area steel 1 plus area steel 2 must equal the total area steel. So I can put here area steel 2, 1.2, and I have area steel total equal 5.06. Then I can figure out the value of area steel 1. It will be 3.86. So far, so good. I will start with part number 1. I have neutral axis here. We have capital C. We have capital T. So I will solve it for part number 1. Part number 1. I said capital C equal capital T. So 0.85 F prime C time A time B equal area steel 1, because we are talking about part number 1, time F yield. Go ahead and put your numbers. We have F prime C equal 3, F yield equal 60. So this one is 3, this one is 60. What is the width of your cross section is 14. The only unknown and your area steel 1 equal, what is the value of area steel 1? 3.86. So the value of A will be 6.5 inch. Keep in your mind, the distance between the two forces will be D minus A divided 2. So MN1 will equal capital T, D minus A divided 2. Capital T equal 3.86 times 60,000 time your depth 24 minus A 6.5 divided 2. Then I can figure out the nominal moment. Divide by 12,000. I got 400 kib foot, 400.6. This is for the first part. For the second part, this part, the distance between the two forces, D minus D prime. I will assume the steel reinforcement in compression yielded. So MN2 equal one of them T, because we have here compression and we have here tension. So one of them T time D minus D prime. Capital T equal area steel 2 time F yield time depth minus D prime. I can put my number, area steel 2 equal 1.2, F yield 60,000. Your depth is 24, your D prime 2.5. Then I can find out the nominal moment for the second part, 1.2 times 60,000 time depth 24 minus 2.5 divided by 12,000. I got 129 kib foot. So the total nominal moment equal 400.6 plus 129 equal 529.6. I can multiply phi mn. It will give you 476.64 kib foot. We need to check. Yes or no. Because if you answer yes, we are done, and this is your nominal moment. I'm sorry, design moment strength. If you answer yes. If you answer no, unfortunately, all of these calculations are useless. We need to remove them and start from scratch using this slide. That makes sense? So let's start to check, and hopefully the answer is yes, but I think no. Anyway, this is your cross section. This is your steel reinforcement in compression, and this is the distance D prime. This is your steel of reinforcement in tension, and this is the depth D. We have a neutral axis. This neutral axis has depth equal C equal A divided by beta 1. I think A is known from here, 6.5 divided by beta 1. I can figure out the value 6.5 divided by 0.85, beta 1. It's 7.6 inch. Keep in your mind, we will have strain distribution, compression in concrete, tension in this steel, epsilon steel tension. In between, we have to pass through the neutral axis here. This is strain 0.003. Keep in your mind, this strain in compression, steel reinforcement compression will have a strain equal epsilon steel in compression. We need to figure out this value. So I will do triangle similarity between this little triangle. Keep in your mind, this little distance will be C minus D prime. That makes sense? And the total distance for the bigger triangle is C. So I can say 0.003 divided by epsilon steel in compression equal C divided by C minus D prime. Go ahead and put your numbers. You have everything. C is 7.6. 7.6. D prime 2.5. The only unknown is epsilon steel compression. What is the value? 7.6 minus 2.5. Find 0.003 divided by 7.6. I got 0.002. I got 0.002. What is the value of epsilon yield? Equal F yield divided by E steel. So F yield equals 60,000 or 60 KSI in this problem. I think 60, yes, divided by 30,000. Let me do something here to make it more attractive. Assume, and you have to follow what is given. E steel is given 29,000 KSI. This value is given here. So unfortunately, I will not use 30,000 because I am given a value for E steel. It's 29,000, not 30,000. If you divide this number by this number, 60 by 29,000, unfortunately, I got, wait a moment. Not 29, I'm sorry. Let me assume it not 29. Let me assume it 32. We are using a type of steel with E steel equal 32, not 29. So this value is not 29. I'm sorry. If this information is not given, you have to use 30,000. But right now we are given a value for E steel, 60 divided by 30,000. I got 0.0018. Unfortunately, your strain in steel under compression is less than epsilon yield. So the answer is no. The steel reinforcement did not yield. The steel reinforcement did not yield. So unfortunately, I have to start from scratch. One more time. Using these expressions in this slide. If the compression steel reinforcement did not yield. Very easy, just I would like to show you how to use these expressions. First of all, I will have compression in concrete, and I will have compression in steel reinforcement under compression, and I will have tension in the steel reinforcement under tension. For equilibrium, this force in tension must equal the two forces in compression, one in concrete and the second one in steel. But keep in your mind, for the one on the steel, equal area steel prime, not time F yield, because F yield, the steel reinforcement did not yield yet. So I will label it Fs prime. So it's very easy. We have steel, a cross section looks like this. I will have tension here, and I will have two compression, one in steel and the second one in concrete. So I will say for equilibrium, the tension in steel reinforcement at the bottom must equal the compression in concrete plus the compression in the steel. This is the meaning of the first equation, capital T equal capital C in concrete plus capital C in steel reinforcement. This is the main idea. This one equal area steel in tension time F yield, because the steel reinforcement in tension is yielded 100%, I'm sure. But the issue with this steel reinforcement did not yield. So compression in concrete equal 0.85 F prime C time A time B. This is a norm. Plus area steel prime time, I cannot say F yield because the steel reinforcement in compression did not yield. So I will call it Fs prime. I will modify this equation more. Area steel F yield equal 0.85 F prime C. This A, I can remove it and put beta 1 C. We have neutral axis. This neutral axis has distance C. If you multiply beta 1 times C, you can get A. So I remove the A and put beta 1 C. Plus area steel prime time Fs prime. I have expression here for Fs prime equal to this expression from triangle similarity. Equal C minus D prime divide C time 0.003 E steel. I'm sorry, C minus D prime. Is it correct? Yes. C minus D prime divided by C time 0.003 time E steel. This is the value of stress in steel under compression, because this stress did not yield yet. So I cannot use F yield. This is the main idea in this case. If you simplify this equation and put every number, you can get a quadratic equation in the function of C. Let's see. Area steel equal the total area steel in this problem equal 5.06 time F yield 60,000. 0.85 F prime C equal 3. Beta 1 is 0.85 times C. Plus area steel prime in this problem, area steel prime equal 1.2. Your C, I don't know. Your D prime 2.5 divided by C time 0.003 time E steel is given 32,000 in this problem. Then I can simplify this equation. I will find myself with one unknown only, which is C. Let's see. So 506 times 60, I got 303.6 equal. This one will be simplified by 0.85 times 3 times 0.85. I forget something here. Yeah, there is B here, should be time 14. We have B, 0.85 F prime C, beta 1 C, this is A, and we have B. Yes. 0.85 times 3 times 0.85 times 14. I got here 30.3 C plus this one 1.2 time 0.003 time 32,000. I got 115.2 C minus 1.2 time 2.5 time 0.003 time 32,000. I got 288 divided by C. We have C here. So if you multiply the whole equation by C, I can get here 303.6 C equal 30.3 C square plus 115.2 C minus 288. If you rearrange the equation, so 30.3 C square minus 303.6 minus 115.2, I got here 188.4 C minus 288 equals 0. You will have a quadratic equation as a function of C. I can solve the C for C equal negative B plus or minus square root B square minus 4AC divided by 2A. I will have two solutions. Let's see. B square 188.4 minus 4 times A times C under square root minus B divided by 2A. I got C equal 1.3 inch. Looks like it's wrong. Let me check it one more time. B square 188.4 square minus 4 times A times C under square root plus negative B. Yes, the second one will give you a negative value. The second one will give you a negative value. Let me check also the first one. Looks like I have a mistake. 0.5.06 times 60. I got this number. 0.85 times 3 times 0.85 times 14. I got this number. 1.2 times 0.003 times 32,000. I got this number. 1.2 times 0.003 times 32,000 times 2.5. I got this number. We are good. So far, so good. Yeah, if you move this one to this side, it will be negative. Yes, let me check it one more time. So 188.4, this is B square plus 4 times A times C under square root plus 188.4 divided by 2 times A. Yeah, 7.4. This number is wrong. That makes sense. 7.5 inch. 7.5 inch. This one will be a negative number. It will not be accepted. So the value of C equals 7.5. Guys, you have to get some logic because this is the depth of neutral axis. I got a wrong number, which is 1.5. Doesn't make sense. That means your neutral axis is still at the top. Doesn't make any sense. So this logic number 7.5 makes sense for me. So once you get the value of C, I can find the value of A, which is equal beta 1 times C. So your value of A equal 5.85. I got A equals 6.4. Also, I can find the value of F prime C, F prime S, I'm sorry, this value. Go ahead and put the value of C, the value of D prime, the value of C, the value of E still, I can find it. So the value of C equal 7.5. 7.5 minus D prime 2.5 divided by 7.5 times 0.003 times 32,000. I got here 64 KSI, which should be less than a field. And that makes sense. This is the main reason why I did all of this calculation. I repeated all of this calculation because the stress in the steel reinforcement in compression did not yield yet. The actual stress is 64, not a field. Oh, the field is equal 60. Looks like we have another mistake here. 7.5 minus 2.5. Divided by 7.5 times 0.0003 times 32,000. No, it's 64, and 64 is greater than F yield. That means we have a mistake. Do you remember what was the mistake? Yeah, here is a mistake. Oh my goodness. I'm sorry, go back and assume your E steel is 29, not 32. I'm not sure why I assumed it 32, 29. So if you assume the 29, it will give you F yield 0.0021. And your epsilon steel yield 0.002 is smaller than epsilon. That makes sense. This is the reason why we answered no, and this is the reason why we repeated all of these calculations. Does that make sense? So this one will be 29. So your numbers will be a little different. This value and this value and this value. Let me recheck. I'm sorry. So it will be 1.2 times 0.003 times 29,000. It will be 104.4. And this one will be 1.2 times 2.5 times 0.003 times 29,000. It will be 261. So this one will be 261. And this one will be 261 also. And this one will be 104.4. Then this number will be a little different. It will be 303.6 minus 104.4. I got 199.2. Then I can resolve the equation. It will be 199.2 square plus 4 times A times B plus divided by 2A. I got Oh my goodness. Wait. 199.2 square. Yes. Plus divided by 2 times A. I got 7.7, a little difference. So 7.7, if you divided it by beta, multiplied it by beta, I'm sorry, your value of A will be 6.5, not 0.4, a little difference. And your stress, if you go back here, you must have something less than 60. If you go back here and put C equals 7.6 minus 2.5 divided by 7.6 times 0.003, 29,000, I got 58. 58. That makes sense. 58 KSI, this is the value of stress in steel reinforcement and compression, which is less than F yield. This is the reason why we answered here no, because the steel reinforcement did not yield, because the strain in the steel compression is less than. I'm sorry for this mistake. Then I can find out the value of MN1 equal area steel 1. Area steel 1 equal the steel reinforcement for part number 1. Do you remember what was? Area steel 1, I think it was here. 3.86. Time F yield 60,000. Your depth 24. Your A equals 6.5. I can find out the value of MN1. Value of MN2, area steel dash or area steel prime equal 1.2. Your S prime equal 58, not 60,000, 58,000. Your depth 24, your depth prime 2.5. I can find out the value of MN2. Once you get the two value of moment, you can add them together to find out the total MN. Then you can figure out the value of MN.